Online, just checking levels. Looking good. Tunage. Also good. Welcome back, friend. Final stream of the year. What a year it's been. My first year of streaming. Pretty okay. Some ups, some downs, some around and arounds. But having a good time. So welcome back. I hope that for whatever holiday or time you find yourself in, you're having a good time out there. That things are okay. And you're happy and healthy. And then maybe you're doing a little Haskell programming these days. You know? So I don't know exactly what to work on today. So I think I'm just going to continue the trend of Advent to Code puzzles. I don't really have anything to review this week because I really haven't done any of them last week. I've kind of taken a break on that. I haven't done a whole lot of hacking. So, but I did finish up the problem a little bit, and I think it might give us something interesting to work on. Because it's too slow. It doesn't run, it doesn't give me an answer in a reasonable amount of time. I'm sure it will eventually. Perhaps, if I'm lucky. But it doesn't yet. So we should probably fix that. And it might be an interesting way to look at how to approach the problem of, making a program that you think you're pretty certain is correct, but it's just too slow. So let's look at that code. Ooh, I don't even know if I pushed it. I'm just gonna make sure I have all the code. I do. Okay. So. Yeesh. Pretty sure that's all. Okay. Let's try it. Oh, wait. Oh, ho, ho, ho. Pretty sure I did this already. Weird. Okay. Well, whatever. We'll get this fixed and then we'll have that part. Okay. That means I've got code lying around somewhere on another machine that I use that isn't committed. Implements this. I think I might be right back, and I'll commit the code up. So we can skip ahead a little bit. The box is frozen. Which is great. Great timing. When things go wrong, they go wrong, right? No worries. No worries. We will recover from this. We'll just fix this test and then we'll be good to go. Really? Okay, so basically, looks like we've got not failing test. We're not getting any data whatsoever. And what are our changes? I think we're working on the step functions, right? Okay. Yeah. Hold with key. Okay. So that's hash map function. And we apply the grid rule to the grid. So the grid here is our prior grid, the one that's at this step. And we pass that in kind of like a constant almost. I'm not sure if we can find that down in our where clause when we apply the rules. But anyways, it's bound as a parameter to our function. We start with an empty grid, and we're going to basically construct the next state, the next grid from that, which is probably why this is unbearably slow, perhaps. That's okay. Pay that no mind. It's okay. It's all right. So let's see here. This test is failing because we apply the rule G to G prime. That's the empty. G prime's the empty grid. C is the coordinate. And L is the character we're matching on. That's the pattern matching now. We get a full key there to do. Let's see. We have the unoccupied rule is applicable. Just G prime of that coordinate to be the sharp. Okay, and then that looks. Test right? I assume it is. Double check that. Test. So all these L's should flip to these. Okay. So for example, at 0, 0, if we fold with key of the empty grid, the input grid there, we get the cell at that spot, L. All right, so at 0, 0, we should get the character L, and this should hit here. And grid is, G is our input grid untouched. We adjust, maybe adjust is not the maybe, at this coordinate. Yeah, so it should hit unoccupied if the unoccupied rule is correct. Coordinate indent, right? According to the tests, I think that's pointed correctly if there is any. Unoccupied. 33. Oh, okay. Maybe with the... No. That one should be unoccupied rule, I guess. Oh, sorry, I got that. Test strings messed up backwards. Reading the wrong thing. So it's occupied. Yeah, okay, so we just returned bool as a guardian Boolean function just to see, like, should we flip this to unoccupied? Maybe, depending on the rules, it's a little bit backwards, but the thing that's bothering me right now is the empty. It might be hold with key. Let me just double check that. Hold with key. Oh, sorry, fold L. So reduce this map by applying binary mapper to all elements using the given starting values. Typically, you have to operate using. The A in this case is going to be a hash map. An empty one. And adjust to see what the part we're doing. Yeah. Okay. That's where we're getting wrong there. So adjust will adjust the value tied to a given key in this map only if it is present. So at the beginning we're using hashmap.empty, so there's no keys in this, so this will always return nothing. Right, so it'll always return the empty hash. What we really want is update. Or maybe alter, but probably just update. Okay. Update, you can be update, and you can be update. HUD-pate. That's it. And of course we don't want a constant anymore, we gotta return a baby A. I think that'll satisfy you. Yep. Let's see. get our match, our test runner going again. Here. Stick, test, file, test docs. Okay. So the idea, I guess, from here, once we get this correct and working, we maybe prove out the example a little bit further with step, that we end up at the right fixed point. That's the right term. But we get there with our solution function, then for a small example, it's fast enough. It's just on the main input that it was too slow. So all we need to do there then is just replace this data structure that we're using with something else. Hopefully we can maintain the same interface that we're using already. We don't have to change too much on the surface to make it faster. Okay. So we're still getting the empty list. We have one more adjust here. Let's fix it. Getting anything? Nothing at all still. Get back. We get empty hash back again. It's no bueno. I guess we don't really need to since we're doing it from the fresh wrap. Maybe we just need to insert. No more tomfoolery. Serious business only. So we don't adjust. But we can just have key in the value, I believe. PC and character sharp. We'll leave it alone. That's just L, and then let's show the opposite basically. Otherwise, we just leave it on. So it's just set. There we go. Okay. So, hash map tomfoolery. I don't know if that's inappropriate these days. Hash map, messing around, stuff, done. Okay. Fast enough in our test suite. But when I tried to write the solution, it was no good because the input's really large. So I'm going to show you what I mean. I'll write the solution, I guess, in part 1. Let's write a little test for it. Could solve the example problem. We'll just call it solve. What should we give it as input? Solve. We're going to have to write a parse function, that's true. To parse our input in. We parse it right into a grid, I suppose. So let's just... write up the example from the site. I think it's pretty large, probably. Copy and paste out. I'll just call it later in that set. This one. Watch if I do it like this. Sample grid. You can give it as a text or a list of texts. That. Bon. I like it. I like it a lot. Oh, yeah. It's good. We'll call it parse grid with our example grid. Could be. What is solve return? Solve return is a number. It should be 37 in the example. Okay, so that won't exist yet. We don't have definition parse grid yet. So let's just go write that in there maybe. Simple enough. Okay. It's going to be from a list. What is that list going to be? It's got to be X and Y and a character. A cell. Where we're going to get those from? Let's see. Well, we got the input list, so we're going to get the rows first and the column numbers. So we'll get the Y. The Y and a row. And zipping together 0 and our inputs. And we'll get the X and the C. Or, I'm expecting it to be a list. So we'll just dirty hacks and call it a day. Have to import data text menu. Maybe it's unpack. Okay, very, very simple parse grid function, up and ready. Whatever. Solve then is all you do in part 1. The solve takes our grid as input and returns a number. It can return a number no matter what is on the grid, so let's see there. Okay. So really all we need to do is solve is step the grid once, compare it to our input, what we already had before, stepping it, and then if they change, we step on the new grid, we solve on the new grid, and if they don't change, we have our solution. We count the number of, was it occupied seats, which I think we have a function for, and then we're done. Okay, so let's get that. Yeah, let's see. Step. How do I write that? Do I want to let bind it? Maybe I want to let bind it. Pull that a little bit left. Let's go here. Okay, so then we have our condition. Grid is basically equal to grid prime. Then we have our solution, so we count the things, else we solve for grid prime. Now this is assuming, of course, that we get to that no matter what input we have, we get to that sort of fixed state. That's why I think when we first started this puzzle, I mentioned that this feels like a fixed point kind of function, or like, it reminded me a little bit of like Newton's method of squaring. You recursively square until you reach a stabilized square root, where the difference isn't too great. It feels a lot like that. Anyways, it might be interesting to go back to this later on and see if there's a way to show that. Anyways, maybe not. Who knows? Whatever. Right, so our whole here, we just have to do our counting thing to return our int, is what we expect. And I believe we have occupied seats function. Right, because there could potentially be no unoccupied seats. Or no occupied seats, like it's just all unoccupied, so this really should be maybe of int. So we can use occupied seats here. Good. our final state, I think. Oh no, that just counts the thing of 1. Yes, this would be just int. We have to write a new function to count through the entire grid all the occupied seats. Count of occupied. So let's go and put that there. Returns an int. Right, so that can be another fold. Fold key script. This time, we just count occupied and starting from 0 on our input grid. So we'll count occupied. Looks like it gets the key, which we don't really care about. Accumulator. So our accumulator is what we can be careful with that, the count itself. We got the value. Key. Yeah, the key. We care the key. So where it's a sharp octothorpe. I like saying that word. Octothorpe. Octothorpe. We count that. Count plus 1. Anything else? And just return the count. Skip over it. Count of occupied. Called it. Didn't I? Not og. Curse you fingers. They're begging for a holiday. Oh, please, we're gonna get RSI. Okay. So, what is this type error all about? IO. Oh, brace size error. It's probably just here. Oh, let's see. It's even slow on this one. I thought it'd be pretty fast on this. Maybe it's going into an infinite loop. Maybe we didn't do it properly. I'm not expecting that. Oh, yeah, no, that would be wrong. No, that's really, yeah, if grid equals grid, then we count. So we should solve for the next one. That seems right to me. So that's kind of what it's doing here, right? We know that our step function works from here to here. Oh no, let's test that out. Thought I had that test already. Probably figured that out of code. Nope, it does step. It does step. Yeah. Well, that's our test grid. And let's test it on the example grid. Just grab that. Ooh. That's not the example input. Maybe that's why. Although I don't think that it's determined. Yeah, no, that might not be why. Let's get our actual method to test with. Step 1. A similar situation. That's the one. I should have gone with this one. There's another famous Canadian once said, doo-doo-doo-doo. Doo-doo. Okay, so this should be result of grid. And then maybe we should just comment that now. Okay, I kind of expected that one to work. And then it should go from this one to this one. So let's just do one more. And I can be somewhat certain that we're on the right path. Pop. Go there. Just copy all of that. We probably have more for it. Probably it's fast enough. Okay. So example step 2. Just to be super confusing. Sorry, future me, if you're watching this. You might fix this later, because whatever. So let's parse the example grid. Example step 1. And that should be the same as example step 2. Okay, good. This would be really handy to have a pretty printer right about now, wouldn't it? So we got a bunch of them, actually, interestingly enough. Wrong. Copy pasted the right second round. Yeah, should be there. Okay, cool. So one way that we're one thing that we're definitely say 9-4 should be we got a sharp. We expected 9-4 to be unoccupied. 2, 3, 4, 5, 6, 7, 8, 9. This one here. 0 base thing. And that one, let's see, that's 4 up from the bottom. This one here. It should go to unoccupied. It's got more than 4 occupied meters around it. Okay, so let's just double check our rule application. Check. There, yeah. Alright, so if we see an L, unoccupied rule says so we're already looking at an unoccupied. There are occupied seats around so there are 0 occupied seats around. So I think we might just have the rules flipped around. So if the occupied seats around it equal to 4, it should flip to unoccupied. Let's just try something. It's kind of neat that it made the first step in the rules having place. Still worked. Oh, that was definitely not the right thing. Not the right thing. Let me just remind myself. The null is an unoccupied seat, right? Yeah, it's unoccupied. It's empty. Okay. So if the seat is empty and there are no occupied seats adjacent to it, it becomes occupied. So if we're looking at this coordinate, we have an empty seat, an unoccupied seat. The unoccupied rule should tell, I think that's what this is supposed to be. So it should tell us that there are no unoccupied seats adjacent to it, it becomes occupied. Okay. This really should be like flip if... I guess it's okay. Right, that's where it gets. So if the occupied seats are on that coordinate, there are 0 occupied seats, then it's true. It should be flipped. Otherwise, don't flip it, leave it alone. Is the seat state does not change. That's kind of what this one's supposed to be here. If the seat is occupied, that's this branch, and 4 or more seats adjacent to it are also occupied, the seat becomes empty. Leave it alone. Less than 4 or more seats adjacent to it. So maybe we just got that sign flipped the wrong way. That's probably it. We probably just have a false test match because we got that test wrong, which is why it was reporting true. Okay. And we should apply the occupied. No, it has only 2. That's right. Okay. So this algorithm goes 2 steps. Maybe the solution part will actually work now. Actually, maybe that was my problem last time. It's actually fast enough, and all of this is just me yammering about nothing. It's been known to happen. Okay, yeah, so it is fast enough. It was an issue there. So let's just run solve again. It solves the example problem. Cool. So let's run that our input. Do. Do something with that input. It's a list of texts, so we'll get our starter grid. And we'll probably just might not be named parse input, of course. It's been a while since I looked at that. What did I call it? read input, of course. Not doing any parsing, just reading it in as a list of text. Okay. Solution. Button doesn't exist. Oh, let's get our puzzle input. Yeesh. Behind the times here. Big. Hopefully it is slow and we can actually do that exercise. That'd be pretty fun. Hopefully it's not as well. That would be nice too. Let's get that input. Put it here. See, it's taking a while. But it does arrive at a solution. Hooray! Let's see if it's the right one. It is. Alright then. I still think it could be faster, but that's alright. We don't have to go overboard with it. Let's do part 2. But if you're curious, how would I approach that? Maybe we can chat about it. I don't know. You can tell me what you think. Well, basically the way I would approach this if it was too slow. I don't really suspect it. You could probably make this faster by making this kind of an array or a vector. But I don't think we'd have to change the interface around any of our functions. We would just have to have an extra function that would translate our x and y coordinate system into an index into our vector, which is a pretty straightforward arithmetic formula for that. And then we would get an array structure. So we would basically, I don't know if it would really speed it up all that much. The only way I could see this being is just reconstructing the hash map. The pure hash map. You know, with an array, with a mutable vector or something like that. Do a little bit there. So they're just not reconstructing a fairly large object because this map can be pretty big. So we could probably bring down that solution. How am I doing that? I think that way is how I would probably go about it. And that way we know the interface is correct, we know the functions are correct, we have the test suite, so we know where we replace things under the hood, and we're doing it properly. So we have a backup solution that tells us whether we're doing it right or not. That's how I do that. On to part 2. So as soon as people start to arrive, you realize your mistake. Ah, rats. People don't just care about adjacent seats. They care about the first seat they can see in each of those 8 directions. Oh no. Now, instead of considering just the 8 immediately adjacent seat, consider the first seat in each of those 8 directions. For example, the empty seat below would see 8 occupied seats. And you'll see this one, 1, 2, 3, 4. I guess it goes on diagonals. 6, 7, 8, yeah. Okay, 8 occupied seats. Oof. The leftmost empty seat below would only see 1 empty seat. But cannot see any of the occupied seats. This one blocks. Empty seat below would see no occupied seats. Also, people seem to be more tolerant than you expected. It now takes 5 or more visible occupied seats for an adjacent seat to become empty, rather than 4 or more from previous rules. Yeah, the rules still apply, though. Empty seats that see no occupied seats become occupied, seats that match up to change, and floor energy stuff like that. Oh, okay. So now I kind of do want to implement that array. Because now we're going to have intersection tests along these axes. Which means we're going to have to be iterating over them in a particular order. And well, we can still do that with our current data structure. Technically, if this is given as a coordinate, we can reverse the coordinate and make it into parts. As one way to do it. All those the lookup time is still a 1 for each of these. Raycasting, essentially, in a way. Very limited raycasting. Yeah. So that... I have my pen pulled. Switch to the left-hand mode. Oh, it's so awkward. Sorry, my pen is mapped backwards for some reason, and I'm trying to flip it back over to the way I had it. I don't know why it switched. Okay. Alright, I'm just gonna have to draw inputs. Something like that. Anyways, what would that look like? So we have the coordinate 1, I have to like increment that way, and then increment the y that way, and then that way, and so on and so forth. Diagonals can be both at the same time, basically like a vector. I'll add a vector to them. Just step the vector at every point. So we get a hit. We want all of the hits in each direction. So that's my awesome technical drawing for the evening, by the way. Super helpful for visualizing stuff. Super important. Great, so we just need, well, we can compose this together, we can do it. We could probably do it with our hash map just fine. Make it make a difference. Random things you find, I swear. Okay. Anyway, you get the gist. Okay, so our grid needs a new function. A function that's going to take coordinate, a vector, and it's going to do a hit test in that vector. So it's going to go along that line, and then if we find a thing that isn't a floor, we will return that thing. I think that sounds about right. So that will be, let's put it down. Here's fine. So, voltage test. Take grid. Take a coordinate. That's going to be confusing. The one thing, the downfall about using tuples is they're all anonymous. Right? Convenient, but anonymous. So then we return maybe, because we could basically go off and it's just all seats, or all floor, and we never find anything along there. Just going to make a type alias quickly, just to make this a little more readable. It's not vector, it'll be 2. I won't new type it, just because I'm probably not going to really define anything else for that thing, but it's good enough for what we need. So, get a grid, we get our coordinate, we have our direction X, our direction Y, and then our goal is to return a baby car. So what do we do? Well, I think we start by looking at the coordinate along the next coordinate along the vector in the map. We probably do this. Let's pull the coordinate apart just to make this easier. Dx, dy, and g, and then we just have case analysis on that character. I'm already thinking that do mistake was a mistake, so I'm going to do that. So in the nothing case, the case is not even in there, we're off the grid at that point. So that's kind of like, not that interesting, I guess. So maybe the do notation was a little okay. Right, okay. So, well, we do have a next. If next It's a floor space. Continue. But it's not a floor space. Just return that. And let's recur. We can make this a new chord. So we do it twice. And just do that here. From our initial XY. Actually, no. That's not quite right. I'd know because if I was smart, I would have written the test for it. No. This should be. We want to continue on with DXD. I'm going to continue on that vector. I'm just going to recur on the next space along it. What have I got here? Oh, okay. Let's call that cell. Cool. So while I mention the test, let's open part 2.spec. To 11. Describe grid, the next generation. Should find the unoccupied heat with the hit test. Okay. Let's take a little test map. We should see now. Let's use this one. Why not? Example grid 1. Let's just make it a grid this time. Reparsing our tests all the time. As we've done. But it's too late now. Just keep going. It's all about speed. We're hacking the planet here. We call it parse grid. Okay. Stop. Do. Hit test. Parse grid. Or example grid 1. So this is how we basically use it. That's its coordinate that is that at. 1, 2, 3, 4. X 0, 2, 3, 4. That should be our L. Three, 4, and our V2 Vector, let's go up on the y-axis, 0 on the x-axis. So remember, our coordinate system starts at 0, 0 on the top left. So negative vector goes that way. Quote unquote. And that would be just survey says. Oh wait, we're not running this test suite yet, I don't think. Let's run part 2's test suite. Cool. I'm a little suspicious though. Let's just make it fail. Now it's not actually running anything. Unless that was a fluke and I just picked it. So 0 examples. Pattern match bad. Oh, yeah, it is. There we go. Perfect. Okay. That's kind of the joy of always calling it when you run your tests. I think this is going to pass. I expect it to pass. I expect it to fail. Sometimes you mess up the setup. Yeah, I just did. Ohio. Okay, and so that's goes that direction. Let's turn one of these into another L so we can test the other case where it matches on a unoccupied seat as well. Those are all occupied seats. Okay, cool. Hit test. Example grid. 1, 3, 4. So this time our vector now should be increasing the x direction. So just make that 1. 0 in the y direction. So just straight across to the right. Quote unquote. Right. Of course, all these are just made up in our head. Up, right, left, down, whatever. Good for intuition, but it's weird to do this for something. Okay, cool. Why did we get a thing here? Cool. Yeah, we should have gotten it now. We got it. I didn't call it, but that's okay. Alright, so what other cases could there be? There's also the case where we only want the first one. So if there's a seat beyond this, we only want to get this one. We don't want to see this one. I should find first. Test. Yeah, cool. This is a lot how it looks like when I'm actually developing roguelikes. I'm doing maps. if I just kind of build a test map. Test all my different game action things. Static. Like this. Yeah, so direction. Move down in X, move down in Y. Same time, so we can take off. It should be just octave. And I expect this one to pass. For sure. First try. Just kidding. Okay, cool. So that's that part. There's our hit test function. The next thing we need to do is just like we did with count, get the occupied seats at a particular point. We now have to get the visible seats from the occupied point. So we'll be able to use this hit test function in order to do that. So we'll call it visible occupied. Is it occupied we care about, or just visible objects? Let's look at our spec again, our requirements. Requirements. So we want visible occupied seats. And visible unoccupied seats. Okay. So they're kind of both the same, so we'll parameterize it a little bit. We'll just call it visible seats. That makes sense. It'll take grid, coordinate, the cheesy kind of way of doing it. There's only really. Let's just make it data string. Occupied. Unoccupied. They're cheap. They're free in Haskell. Just use them. Why not? Seed state. We could probably write a function to interpret that down to our character. In order for us to mention it if we need to or not. It's fine. Anyways, it takes a seed state, whether we're looking for visible occupied seats or looking for visible unoccupied seats in our grid. And then it returns just like occupied seats. Integer. Maybe integer though, of course, because of the whole grid coordinate problem. Okay, visible seats. Let's implement here. I think that all makes sense. Third, seat state. Okay. Visible neighborhood. Sort of like our neighborhood function from before. So that we're going to list of, instead of list of neighbors like this, we're going to do a list of things. So that's kind of interesting. Neighborhoods don't necessarily have to be implemented like this. This is a very concrete implementation of what a neighborhood is or what it means. There are lots of different kinds of neighborhoods, as you can imagine. I'm just going to write visible neighborhoods. I'm not going to get into that, but you can make a generic version of this. I can take my spec for what a neighborhood is and give me a neighborhood function in return. That would be nice. If I was going to build out this grid API, that would be super sweet. Can I go with the OR spell? Okay, grid. I think this is almost going to be worth it. And we just make sure that it's on the map. This somewhat similar, except I don't think we're gonna have to do these H lookups of cat maybes and stuff, since we're gonna be using our hit test function. Oh no, it does return maybes, so yeah, we will have to do cat maybes. That whole business. In fact, it's yeah. I'm just gonna bite the ball and paste it in. So it's pretty much the same. The only difference being is that instead of h.lookup here, we're going to be doing hit test. Actually, probably just replace that whole file. And this. I need a grid to all of them. Still 8 directions. But this time, instead of giving explicitly the coordinates, we're going to give the chord, and these will be all our vectors. Grid. Those like the first parameter. We just have x, we basically get 0, we're not adding anything to x. Zero. Just 1, 1, 0, 1. Last. Okay. Super good copy times. Visible neighborhood. So that'll be good for visible seats. So get the visible neighborhood. Auto grid, add a coordinate. We might get a non-empty list of characters. And this time we're going to count visible seats. With our seat state. If we count our visible seats, that's going to take a seat state. Take non-empty cars. And of course, I think that's going to be all good. So we'll just type checks. Oh, I forgot to return here. Oh, right. Forgot to get the original coordinate. So we don't actually need to pull apart the coordinate for this time, so we'll just do C. I don't think we use that in here. Yeah, no. Happy now, hit test? Okay. Some formatting fun. Okay, those are a little redundant. I was just being paranoid. Expression is totally motion. All right. Okay, so if we get this right, let's, for example, so then seats, red, one, 4. And we need to give a seat state, so let's give it occupied. And that should be. Well, we changed one from the example to unoccupied, so that should be set. Just so. That won't compile yet, because we still have enough fun to do. Should. Alright, but we tap here. You know. Right, it's gonna throw an exception, so they'll still compile. Blah. So let's go implement count visible seats now. We have it. And geez. See, this is why my fingers need a vacation. They're losing their way. Getting burned out. Okay, count visible seats now. So basically, when we match occupy, we're going to basically take our fold had before from occupied seats. Just a little bit different. So if the character is a hash, there's two cases we want to do count visible seats on. So let's pattern match out seat state. Occupied for this one. And then the second case, the unoccupied. In that case, we don't want to count this character, we want to count the L's. That's it. And that passes it. Cool. Okay, and just to be doubly sure, this is the kind of downfall of unit tests I found, is I think you would each example laboriously and test it one at a time. Visible occupied and visible unoccupied. That should be just one. Oh, that's good we didn't change this here. Man, good stuff. Loving it. What do you think, chat? Pretty good? Pretty good. Pretty easy so far. Pretty straightforward, I hope. If anybody has any questions, of course, feel free to type in. If you want to know something, just ask me. Happy to talk about what I'm doing and what I'm working on. Answer anything I can. Okay, so that's all the visible stuff. So we just have to implement the new rules, I think, for this solution. And then we're good. Now, this is kind of like, just like with visible seeds, visible neighbors, there's a lot of repeated stuff here. We could really generic up this to the 9s if we wanted to. But, let's see, we're running 15 minutes. Let's see if we can get the answer before we get a run. Okay, so in a similar fashion, this should terminate as well, I guess, once we reach a point where it doesn't change anymore. Okay, so that would be a new step function with a couple of new rules. Visible, unoccupied. Occupied. I'm just returning some bool. We're just asking a question. Should we do this or not? And visible occupied. We'll have to double check. The rules, I think they're slightly different. We're going to implement them in here. And what else? A step. Kind of like part 2 step, I guess. Grid to grid. So again, you see, you're gonna see, like, this is almost, except for changing the terms, the structure is the same, which is why it's a good, I think, a good candidate for a generic framework here. So get a grid. We have pull with key. Pull down with key. Again, we're just using slightly different. I'm going to copy and paste this here to here. We rename term goes here, so this is just unoccupied. This is going to be visible. Unoccupied. This is just going to be visible. Occupied. Otherwise exactly the same. I think that's my theory anyway. Okay. So let's just double check our requirements again. Okay. Yeah, so that's all the rules of seeing. So it takes 5 or more visible occupied seats. For an occupied seat to become empty. Rather than 4 or more. Okay, so the other ones are just pretty much the same. It's just this one that changes. Visible occupied. Grid. Chord. Again. Stand. I'm just gonna jump and face that as well, because why? And I'm just seeing where. Instead of occupied seats, we're gonna use visible. Our visible. Generic visible seats function with our occupied state. Boom. But then the rule changed a little bit. It's just 5. And this one, unoccupied, remains the same. Go. Let's get our grid coordinate. And change this to visible seats. Unoccupied. Cool. Good. I like it. All right. As before, let's just write a test for our step. A couple of them. Should step the example. Do that. Call the visible step. Grid. Could be. Example grid 2. Grid. Note to self. Write more Haskell statements. And let's go grab that. this starting layout. Example over the grid 3. Feeling pretty good about this one. I think we're going to end up getting this one on the first try. Place your bets now. Booth closes. Next step should be this one.
Maybe it's time we all gave evil a chance. Even the devil needs a friend.
Okay, cool. Sorry. Oh, he called it, but it didn't. Didn't go. Didn't go burr. Let's see. Everything is still... Nothing changed, it looks like. Visible step. This was step. Yeah, maybe we got these flipped around. It's the number of unoccupied seats, right? That we should be looking at there. Occupied seats. Let's put occupied seats. Yes, occupied seats is looking for octo-door. And visible occupied seats should also be looking for octo-door. So greater than or equal to 5. Should be good. Visible occupied seats. Occupied seat empty. So we know visible seats works, and we know it's going to return us the visible occupied seats from this coordinate. Visible unoccupied should be just the same. Once we match on an unoccupied seat, and we're checking if we should switch it to occupied. So we look at the visible unoccupied seats. Oh, it is a bit of a confusing nomenclature, I say, actually. deeper. So we match, we're at a cell with an L. We look at the visible, this function here, which just makes sure that that coordinate's a valid coordinate in the grid. So let's assume it is. We're looking at an L. So we're matching on just the L here. If it is just an L, we look for the visible unoccupied seats. And if there is no unoccupied seats next to us, then we should return true, or which means we should be flipped to occupied. Probably replace this bool with our seat status. And remove a little Boolean blindness from this code. That would be a good factor for that, for sure. So I think that's right. And if we get to occupied seat, we have more than equal to 5 occupied seats. We should return true and flip to unoccupied. Yeah, that seems good to me. Did I copy the wrong grid? I don't think so. Okay, well, let's tear it apart then, I guess. No solution for us tonight. We'll go a little tiny bit later, just because it's the last stream of the year. My gift. Why not? If you're up for it, I'm up for it. Okay, so some reason we are not returning the next step that I expected. Now we have specs for a lot of the little parts, visible seats. That should be right. What else could we be missing? That we haven't tested yet. The neighborhood function looks good. Is it maybe visible seat? Check our requirements again. Maybe we missed something with it. Okay, so leftmost, we'll see one empty seat. Right, so this one here can only see the one empty seat. Can't see any of these. We've got a test case that does that. So our visible hit test function can check that. Empty seat below, let's see no occupied seats. Also, people saying the following visible occupied seats or an occupied seat. To become occupied. From our existing state, we have occupied. We how about the other row still apply. Empty seats that see no occupied seats become occupied. Since matching rule don't change, and floor never changes. I think let's see. Okay. Let's just double check visible neighborhood. I mean, visible neighborhood is used by visible seats. I'm trying to think if there's an edge case or something there that we're not catching. What could we think of here? Well, let's get another example grid. Say occupied seats. A visible neighborhood's implemented wrongly, no, by using the seats on our edge case. Visible seats needs a coordinate. We'll have to bring this back probably. Let's go. Make an edge case. Well, from example grid 1. Got this here. We've got a test that already finds the 7 occupied seats and has this one in the right, so that's kind of the edge case I was thinking that would maybe trigger what's going on here. It's occupied and unoccupied. We've got tests that cover those 2 cases. The other case is like the completely empty grid, completely full grid, which should just return 8 of whatever one we're searching for. Our neighborhood function only looks at the 8 directions. 2, 3, 4, 5, 6, 7, 8. No, so it's not counting itself. Here's our test. Let's see. do physical seats. Occupied should be just 7. Yeah. So, and we're doing that on example grid, so we're using it right now. Alright, so if we're doing that count on that grid, looking for occupied seats only, and we get 7. If there was an edge case where, I don't know, somehow we were not calculating the vector right, or counting this one as well, or not. The hit test even blocks and checks that as well, so not double counting anything by accident. Physical neighborhood gives us 8 things that we find with our hit test. So I'm not even sure if, even if we try to come up with a test case to see if maybe hit test is counting the coordinate it starts at. Maybe it could be that. So let's try an example where we could get that. Test edge case. Test, we'll just call it test 1. And this one will just be simple. Let's just have a grid. It's just one element at 0, 0. Say an octothorpe. And we do a hit test in any vector, we should get 0. Or nothing. We should get nothing. And if it was misbehaving, it was counting itself, like the element at 0, 0, that cell, then that would be a mistake. I don't think this is going to be a problem. Because the other tests work. Just trying to narrow things down here. Test 1. 0, 0. Heading in any direction, doesn't matter. Could be nothing. So let's get rid of that. Try it again. Okay, that one's failing. That one... Yeah, so it doesn't. That's weird. It should literally be step, just with different functions. What are we missing? Oh. Okay. Like these are not, these are exactly the same. This is something, folks. Did I get bad input, maybe? Ought to be nice. I think we tried this one already. That doesn't sound right at all. It's not, of course. All right, so I'm just stabbing at things, trying to see if it'll pass. If I'm just flipping some things around. Oh, look at that. It did. Okay. There you go. I just got them in the wrong place. So I wonder if Boolean blindness is just a fact that you have a sum of two elements. That's it. An enumeration with two elements. Or one is the opposite of the other. It doesn't matter what they're called. True, false, occupied, unoccupied. Yeah, the wording in this code I think could use a bit of cleanup to make it a little bit more understandable about why it's working. Okay. If this does work, then I suspect the solution for 2 going to be, again, exactly the same. Just slightly different. So, I'm going to close part 1, get part 2 open, up and off. You still want to get the count of the occupied seats at the end, I believe. Occupied seats. So instead of step, we use visible steps. And the same as before, if greater than the prime, blah, blah. Okay, cool. That was actually pretty fast. And oh no! It's not the right answer. Your answer is too dang high. Okay. Cool. Cool. Interesting. Alright. What could it be? Alright. It could be that my fix for the step function wasn't actually a fix. It just fixed it in case. So maybe if we go back, we add, like we did with part 1, the second step from the second to the third, and that will reveal the error of our ways. Okay, so that's that one, we've got that one, so let's get this example here. Grid 4. Let's test your step. It should step again just fine. So let's take a visible step from example grid 3. And that should be example grid 4. Hopefully this will actually fail. Excellent. It did. So we got a bunch of octothorpes that were supposed to be hells open. Yeah, so I think my fix that was a fix was not actually a fix. Or whether I'm misinterpreting here. I suspect if I flip them back, that maybe this test will pass, but the other one will fail. And that might maybe. What's going on? I'm not sure. Go back to grid. So, all I did was flip these around. Silly poking around until the tests pass. Style of development. Yeah, we got one failure. This time's the other test, just like I thought. Okay, so something fishy about the rules as implemented in our code is the problem. So if we flip the visible seats function from occupied to unoccupied, it makes those two cases flip. One's correct and the other one's not correct. Which means if I change the value in that term, then I'm still going to have the same issue. If I change this 5 to what the rules claim, it should be, maybe it's not greater than equal to 5. Maybe that's my problem. Let's go to requirements. One last time. Now it takes 5 or more. Yeah, so greater than or equal to 5 for an occupied seat to become empty. So the visible seats around that seat's coordinate. Are occupied. That, like, dang, that doesn't make any sense. It just doesn't. I shouldn't be able to, like, if I change that to 4, I should totally break both of them. Alright, 2 failures, yeah. Go from the one that's failing now is the one from step 0 to like from here to here. This one's failing. This one to this one is fine. So what the heck? Planet Earth am I doing? What is going on with this test? With this case? Like initially, when we call visible neighborhood, it should just be this almost exactly this function. The only difference is that we're going to recur on hit test instead of just look up the next one. And hit test finds the first thing. So we start at 0, 0. We get 1, 2, 3. 3 unoccupied seats, which would turn it into an occupied. Yeah. And 0, 0 is reading it as unoccupied here. Even all. Except for the 4s, those are fine. We look at the unoccupied seats. If the number of unoccupied seats is 0, that makes sense. We should flip it to this. Wonder what visible seats is returning at 0, 0. For example, grid 2. Let's just run a quick test for that. Find 3 unoccupied seats. 0, 0. Hopefully this fails. Be helpful. Okay. 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 That's something. So example grid 1. Oh no, of course it would. Sorry, I meant example grid 2. Dang. It's getting hopeful there. Hopefully it fails. I'm not so sure it will this time though. Shmup. More shotgunning. I could flip those around. Hopefully not break anything else. Well, now it works. Okay, you must have read the requirements wrong. Go back to solution then. A little more confident in it this time around. I should have been suspicious when it went so fast, I guess. Means it probably like didn't try too many iterations. So this one I bet will take a while. Hopefully we don't actually have to, I don't actually have to do that optimization. That we were talking about at the very beginning that we thought we would be spending our time on today. Well, maybe we should have. Ooh. We might be waiting here a while. If that's the case, it's getting late, so I'm gonna have to leave it as homework. I'll leave this running to see if it does come up with an answer. But I'll push this code up, and if you want to take a stab at trying to make it faster, let me know. Fork it. Make a pull request, or keep it to yourself. It's cool. And I'd be interested to check that out, how you approach it, and what you do. Hopefully it's correct. So as long as it's correct, you can make it faster. There is a way. That's a clever... It must have been tricky to develop that puzzle. Maybe. Or at least to generate the puzzle. I don't know. Maybe not. But it seems like it could have been pretty fun to develop that one. Push that up. Voila. Well, my recommendation would be to add tests like we did for part 1 to at least solve the example on the front page before attempting this on the input. But if it is an optimization problem, that'd be a fun one, and I'd really be interested to see how you tackle that one. I'll probably try it myself, and we can compare notes, which we'll probably do in the new year. So I'm not going to be streaming Tuesday next week. I think that's probably a no-go. I might take a break. I think it's Tuesday next week. Well, it's only the 29th, but yeah, I'm not going to be doing streaming next week. So, break from me. Thank you for a lovely, wonderful 2020, and for letting me stream and tuning in, and watching my projects grow, and watching me learn. And I hope you've learned a few things along the way as well. Looks like 2021 might be a good year for Haskell. Things are turning up, building up. A lot of interesting releases. Haskell IDE engine has been coming along so fast. And some good libraries coming up from folks. I have some ideas for ones that I would like to to have for work, which, I don't know, maybe we'll work on those together at some point, or maybe I'll just hack it together and show it off sometime. But may all your monads be free, may your types always check, and as always, have a great time hacking Haskell. See you later.